Hello students, I hope you remember that in previous class we had discussed how we can obtain coherent beams of radiation, and there were primarily two general methods. First one was wavefront division, and second one is the division by amplitude. So now today we will discuss them one by one. So first method is interference by wavefront division. And why we need this, why we have these two options? Because we need a coherent beam of light, and for getting a coherent uh, sources of light, the two sources must be actually derived from single source. So that is what is achieved with the help of these two approaches, say by wavefront division or by what you call this uh, division of amplitude, wavefront division and amplitude division. So now we will be starting with the wavefront division method. So what is the idea of wavefront division method is that if we have a wavefront which is emanating from say a single point source, then we know that all the points on the wavefront are in phase with each other, correct? Now if we take any 2 points from the wavefront and make them the independent sources by themselves, and how will that happen? We can I think go back to the Huygens principle. So if you see this one, so in this case we have a light source which is emitting light. It's a point source, suppose. Then it is emitting light, sort of a spherical waveform, and these lines are representing the wavefront. Now each point on wavefront is having same phase, and obviously since the light is coming from single source, so of course it is going to be monochromatic. We are making sure that the source is actually monochromatic. Now if we place arrangement of two slits in the path of this wavefront, so what will happen? Only 2 points. If the slits are very narrow, then only something like two single points will be allowing the light from this whole wavefront to travel further. Other portions or the light from other portions of the wavefront will be blocked by this slit. So these two sources, if we go back to Huygens principle, can be seen to be like 2 point sources, but now derived from the same source. So these two sources are having same frequency, same wavelength, and of course same phase as well, because they are derived from 2 points on the wavefront of the same source. Now since these two are the point sources or very narrow sources of light, so what will happen? Let us assume these are point sources. So in Young's double slit method, actually he started with a single narrow source and then pinned two holes in a slit from which he could produce light, and from that light interference pattern was seen. So if these are single point sources like single holes, in that case what will happen? The light coming out of these two sources would be spherical. The wavefronts coming out of these sources will be spherical in nature. So this may be even slits. You may take linear slits. So we'll be discussing that in the coming slides. But anyway, let us assume these are two sources. So what will happen? They will be emitting light further. The light will be propagating as if that is coming from the point source from here as well. And when these two rays interfere with each other, they produces what is called the interference pattern. So this way of obtaining interference comes under interference by wavefront division. Why is it so? Because we are dividing wavefront into two sources, and then further those two sources are acting as the sources for causing interference pattern. Now let us discuss Young's double slit experiment in theoretical detail. So this has been taken from this book. So again we have suppose this has been done in the previous slide as well. This is a quick overview, since we have this topic was given in a better manner in this book, so that is why we had to switch over to the notations. So some of the notations are different than the one which we are following in that book, which is being followed in the previous lecture. So, so let us do a quick overview, quick revision of this book's way to describe the interference. So suppose we have two sources, and the electric field out of those two sources. I mean, suppose two sources of light, so they are say suppose radiating light along say K1 and K2 direction, and in that case, two beams we could say actually. And the electric field can be written to be like this, where K1 is the wave vector of the first one, K2 is the wave vector of the second one. So this is like general approach. Here we are not saying okay the two sources should have same wavelength. The frequency is same. So wave vector are different actually. I mean the wavelength means they may have same wavelength in case the magnitude of K1 and K2 is same, and frequency is same. So we are saying the two sources are monochromatic and are having same frequency. And suppose epsilon 1 epsilon 2 are the initial phases of the two sources. So the intensity will be given by say time average of square of the electric field, where what is the electric field? It is coming from the overall electric field, which is coming from the superposition of the two. So you can recall that image, 1 K1 coming, say second vector K2 going like this. So both superpose. What will be the resultant electric field? That will be so E square. Let us first find out. E square will be E vector dot E vector, and what will be E vector? E vector will be nothing but E1 plus E2. So if there are only two waves which are superposing, so that E square will be this E dot E, and this will be just nothing but very simple dot product of the two vectors. We can find out it, and we can represent in terms of intensity this as say I is the total intensity, I1 plus I2 plus I12, where I1 is the first term which is coming from this part, and actually this is not directly the intensity. This doesn't give intensity directly. We have to take time average. Fine. So for intensity again, I1 intensity of the first source is going to be time average of square of this. Similarly I2 time average of square of this, and so on. So let us first try to calculate E1 dot E2. So E1 dot E2, you know E1, you know E2. So you can evaluate this very simple expression, and I'm leaving it to you. So it's given in this book, and then you can find out how they have simplified it. This will be cos C plus D formula, and further simplification will be there. So anyway, so the time average will be following using this formula, where this time average of any function, say suppose we have a function which is evaluated up over a time period, over a time say t, then time average will be given by this in sinusoidal and cosine function. So because we have to find out time averages of all these three quantities, so we will be actually coming across time averages of cos function or sine function, right? Because their product will also give us some sine terms. So and by using the formulae for these time averages, which I believe you have done in your intermediate classes, I think that okay, time average of cos square function over a time period is equal to half. Similarly, sine square function for a time period is equal to half again, and cos omega t sine omega t, the time average of it comes out to be equal to 0. So you can try to go back to your uh, uh, previous classes notes, and then from there you can try to have a quick revision of this. So once we simplify this and use these values of time averages, we can find out that time average of e1 vector dot e2 vector will be equal to half e01 e02. So these amplitudes of the electric fields, and cos of k1 dot r plus epsilon 1 k2 dot r epsilon 2, right? So this is coming from simplification of this. So you can use simply cos say 2 cos a cos b, right? So you can try to find out what is the formula. I leave it as an assignment to you, so you do it. So 2 cos a cos b will be giving you something like this, or CD formula, I believe, cos c cos d. So this half factor is coming because of those formulae. Now we can write down I12, this term, as say I12 is equal to, this is time average now, fine. So this is equal to, so I12 means we are saying E1 dot E2 into 2 is I12. So because I12 has that built-in factor of 2 here in the product, so that is why this half cancels with that, so that I12 is equal to E01 E02 dot product of the two cos of delta, correct? And delta is nothing but the difference of the phase difference between the two. You can try to see it from here. So k1r is the phase of the first. Omega t is same in both, so it will cancel. K1r minus k2r, so k1r minus k2r is coming from this part, and epsilon 1 minus epsilon 2 is coming because of their initial phase differences. So this one is the net phase difference. Now let's, you should recall it from the previous lecture, that concept of uh, plane of polarization. So now in case the simplest case is, say the plane of polarization of both the beams is same, so that they are parallel to each other. That's the same thing which we had used in the previous lecture, right? So in case they are perpendicular, there won't be interference. So for two beams to show good interference, their plane of polarization must be same. So that I12, therefore we have written to be equal to this. So now these vectors has disappeared, and their magnitudes have taken the place because they are parallel to each other into cos of delta. So that is the interference term actually, which leads to those maxima and minima. And similarly, I1 will be E01 square upon 2, this factor of half, coming because of cos square factor when we will take product of E1 with itself. So you will be finding E01 square, cos square average of time average of this is going to be half. So that's it. Similarly, I2, so that I12 is equal to, can write down, we can just simplify here by using these two. So this I1 I2, if I take I1 I2, product of I1 I2, this will be E01 square into E02 square upon 4, right? And what we need is actually E01 E02. So for that we have to take the square root. So this multiplied by 2 would give you this one. So I12 is equal to 2 I1 I2 under the root cos of delta. This is pretty simple rearrangement of the terms, so I am sure you can do this. Now therefore we can write down this total intensity. This already we have done in the previous book, as previous lecture as well. This is a quick revision just to make sure that you don't get confused because of change in notation while going from one book to the another one. So this is what is the intensity, correct? And what is the condition for constructive interference? Of course, this phase difference must be 0 for constructive interference, 0 or plus minus 2 pi or plus minus 4 pi or so on. And what will be the magnitude because of constructive interference, or I would say the highest intensity actually because of constructive interference, that should be given by this, correct? Similarly, destructive interference, the condition for destructive interference is this one. You all know this because cos of delta is minimum at plus minus pi, plus minus 3 pi or so on, so that the minimum intensity will be given by this expression. Now let us try to imagine the case of, this is general formalism as far as till the discussion till now is concerned. Now let us assume that we have 2 point sources, as in the case of Young's original double slit experiment. Suppose you have 2 point sources which are derived from one single source, of course. So in that case, source S1 and S2 will be acting like sources of spherical waveforms. So now the whole formalism discussed above, we have to discuss that in context of spherical waveform. Okay, let me go to previous slide quickly. Yeah, so here one thing is very important to notice. This one is representing a plane wave as long as this is constant, correct? Now every else thing will be continuing, but if we apply the idea of spherical wave, then the amplitude of electric field, that E01 and E02, will no longer remain constant functions of time as well as the position in the space. Therefore modifications have to be done there. Okay, for time being, okay, let us still focus on this part. Say this part, let us say, okay, both the sources have same intensity, and let the value of intensity is I naught for both. In that case, this expression for intensity simplifies. You just have to put values of I1 and I2 to be equal to I naught, and this will be equal to this, and then we can write down 4 I naught cos square delta by 2. So note this expression, we will be needing it in the coming slide. And I think same expression we had obtained in the previous lecture, and notations may be a little different, so try to compare your previous notes with this one so that you don't get confused that we are doing something totally different. It is same thing as of now. Fine. So that in this case, whenever intensities of the both sources are exactly same, I minimum will be 0. So you can put here, this is going to give you nothing but 0 value. I mean, this is I naught plus I naught minus 2 I naught square, so 2 I naught. So this will give you net minimum value of intensity to be 0, and I max is equal to 4 I naught. And that's the situation when we have that what you call fringe visibility or fringe contrast 1, right? Otherwise, if that is not 0, here a factor of gamma also sits. I hope you remember that. Okay. For point source, the electric field will be spherical. Now let's come to this story which we want to discuss here. So we will be using this part now, and the other formalism will be modified for point sources. Now in that case, our electric fields now will be the amplitude part will be functions of r, and you know what is this for a spherical wave? This is E01 divided by r1, E02 by r2, something like this. R1 and R2 are the radii of the spherical wave fronts overlapping at. So suppose okay, this is say spherical wavefront coming from source 1, spherical wavefront coming from source 2. At some points P they overlap, so R1 and R2 are the radii of those spherical wavefronts, and it is actually the overlap of those two wavefronts at a certain point which will decide whether there will be a maximum or minimum, or what kind of interference pattern will be observed. So now delta, in this case the phase difference will be what? So phase difference will be the difference of these two phases, correct? Omega t cancels, because what we are assuming is that both the sources have same frequency, temporal frequency is same. Now in that case, and wave vector, I mean the wave vector is also same. Wave vector means the magnitude of the wave vector, means wavelength is the same. So therefore difference of amplitude will be k into r1 minus r2 and epsilon 1 minus epsilon 2. Correct? Now if the size of the screen is small, means okay, two spherical wavefronts and the screen which we are taking is not very big in comparison to the separation of the sources and position of the screen. The screen is not very large in that context. Then and the observation point is far away from the sources. This P is also far away from these two sources. What we can do is we can assume that the variation of intensity of the radiation over the size of the screen, we can take it to be almost like constant. Means this values of intensity, we can take them roughly to be constant and not varying so strongly with R1 or R2. This is just a simplification, but the spherical part, the spherical character will be sitting here. So in that case, what we can obtain is, okay, again same the approximation, say I1 is equal to I2 is equal to I0. Then we can find out this is the phase difference, and remember that formula, I is equal to 4I0 cos square delta. So delta is now half of this, this was cos square delta by 2. So this is delta. We just substitute the value of delta here and then we find out I. So that will be 4I0 into cos square of this term. So you can note it and then we can write down this. This is simple. Now we want to obtain condition for maximum intensity or condition for maxima. When will that happen? Whenever this term leads you to what? This is equal to, or whenever delta is 2 pi m. Why this is 2 pi m? Because there is a factor of half as well here, as well as, I mean the factor of half is sitting here. So otherwise if you go back to the previous condition for maximum was, it has to be this one, 2 pi plus minus 1 pi plus minus 3 pi was condition for minimum, right? But here delta has to be 2m pi, condition for maximum. Now phase difference has to be, okay fine, 2 pi m, that is fine. Now minimum, for minimum intensity has to be 0, and what should be the phase difference? It should be pi m dash. Say m and m dash are some integers, just m dash has been chosen to be different notation to represent them irrespective of each other. Now okay, condition for maximum. What will be the condition for maximum then? What you can do is you can just put this value, which is delta, to be equal to 2 pi m. So if we put this value to be equal to 2 pi m, what we can find out is, from there the value of r1 minus r2 must be equal to 2 pi m plus, say, e2 minus e1. This term has gone to the other side, so basically we have put delta here and rearranged the terms. So there is a multiple of k, so k is going down there. Therefore condition for maximum will be this one, and similarly we can find out the condition for minimum to be this one. If the waves are in phase at emitter, let us now assume that from the point where these waves are being emitted, and since we are following, say, a wavefront division here to obtain the interference, then definitely the waves on different points of the waveform are already in phase. So we can say in that case this epsilon 2 minus epsilon 1 will be 0, correct? and therefore the condition for maxima becomes R1 minus R2 is equal to 2 pi m divided by k, which has to be nothing but m lambda. So how lambda? I mean, it just came from this. We substitute value of k is equal to 2 pi by lambda. So this is just m lambda, and this is the condition for minimum. This is equal to half m lambda. So you try to recall. I mean, this is just path difference. R1 minus R2 is nothing but the path difference. So this is showing that okay, if the path difference is integral multiple of wavelength, then there will be a maximum, and if it is integral half integral multiple of the wavelength, then there will be a minimum. Now in context of present geometry of the experiment, that is what is going to be observed experimentally. So suppose this line is representing the line on which two sources are located. So this is first source located here somewhere, and this is second source located here somewhere. Correct? Now what about this condition? R1 minus R2 has to be a fixed number. Lambda is fixed as far as you fix the wavelength of the light or source of the light. This is fixed, this is fixed. So right hand side is totally fixed. So R1 minus R2 has to be a constant number. R1 and R2 are two vectors. For spherical wave, they can assume any value, right? Now suppose this is R1, this is R2, correct? Now suppose they satisfy this condition of maxima. So this is equal to m lambda. So it is not just this unique plane in which this R1 minus R2 is equal to that constant value of m lambda is satisfied. Actually, this condition is satisfied over all the points on this say paraboloid where this condition will be satisfied. I hope you should be able to visualize this. So I take this any point on the surface of this paraboloid, you would see this is R1, this is R2. Their difference will be following this equation. Why? Because the difference of two vectors, what is it going to be, or sum of two vectors, depends upon their magnitudes and angle between them, correct? So as far as those vectors are lying in such a way that they are on this surface of this paraboloid, the angle between them is going to remain same. So in this case, this is the angle, right? In this case again, the angle between the two vectors will remain same. You try to put some imagination in this figure, and I'm sure you can just figure it out. The other way of looking at it is something like this. Suppose you have one vector, let us assume is like this, say vertically, say upward. There is other vector making angle theta with this, correct? Try to draw this figure in your notebook. One vector vertically upward, other one making an angle theta with it. So what will be their sum? Some given number, you can apply that parallelogram law and all. Now these two, the sum is fixed. What we are saying is sum of the two vectors or difference of the two vectors is fixed. Now it's not, the location of those vectors is not necessarily I mean the unique one. As far as those vectors are making that constant angle with each other, their sum or difference will remain the same. So what can be the other choices? You take first vector, keep that to be vertically upward, take second vector on anywhere on a cone, correct? Making an angle theta. So you try to imagine that to be like a cone, and first vector is representing axis of the cone, second vector is along you should say surface of the cone. So as far as the second vector is on the surface of that cone, this should be able to maintain that product to be a constant number. Fine. Similarly, this difference can be satisfied accordingly. So what we should observe is that the maximum, if we try to put screen here, what we should see, I mean if we try to put the screen in such a way that it is perpendicular to the um, axis containing the two sources of light. In that case, on that screen, the interference pattern will be circular in nature, right? So this is first interference circle, this is second one, third one, and so on. So for spherical sources, if you have 2 point sources or two spherical waves interfering with each other, now depending upon how the sources are located, if we take the screen perpendicular to the axis of location of the two sources, then you would be obtaining the circular pattern. But what happens when you observe the same thing on a plane? Okay, now suppose we are trying to see the interference pattern on a plane containing the two sources. In that case, what you should see, you may see, okay, you have a maximum somewhere here, then one thing is that, okay, now if you have a maximum here on this plane, then you rotate this plane through 180-degree, the maximum will remain on this position. Means the interference pattern has a cylindrical symmetry, you would see, right? So it will be having cylindrical symmetry. So you will have, say, if you see along this, how would be the interference pattern? So there will be a maximum on this plane, suppose. There may be a minimum somewhere, there will be a maximum, minimum, and so on. So means if you see the interference pattern on a plane containing the two sources, two spherical sources or 2 point sources, sorry, the interference pattern will be the lines, right? Like we had seen in case of interference of two plane waves. And if we see or put the screen in this way, we will be seeing them to be circles. I hope you are able to imagine this. So that is what is going to happen. Okay, so depending upon how you are placing the screen, the interference pattern because of two spherical waves will yield you different behavior on the screen. And now let us discuss that Young's double slit experiment in the conventional way, the way we used to do. So basically this situation, this is what you discuss it in most of the textbooks, how you discuss Young's double slit method. So basically this refers to, so what you should see here on the screen. Now, okay, I ask you to pause this video and try to answer this question. What should be the pattern of the interference? I mean, what should be the shape of the interference pattern on the screen? So, okay, now if you have done that exercise correctly, we should see that this should be what? The straight lines like this. The interference pattern should be patches like this. Why so? Because in this case we are trying to see the interference pattern in a plane containing the two sources. So this plane is this is suppose is the plane in which we are doing study of interference pattern. So this plane contains two sources. So in this plane, if you place the screen, you should see the straight line or linear fringes. If your interference screen would be somewhere here, if your screen is somewhere here in a plane perpendicular to this line containing the two sources, in that case on that screen what you should see, the circular fringes. Correct? I hope I could make it clear to you. So now this is just a quick overview of the conventional discussion of Young's double slit experiment. The phase difference in this case delta will be just k naught into r1 minus r2, the same. So where r1 and r2 are the distances of say this point from source 1 and source 2. That's how you used to do in the conventional way. You can go back to your plus 2 books, or this is a very good source from where I have picked this up. So you can go and then do a quick overview or quick revision of this. I will be just showing you quickly how what we have discussed till now. This one is related to what you have done in your previous classes. You should not get confused. Oh, in our previous classes the interference pattern was so easy, and now it is just a mess. It's not like this. Now what we have done is a generalized overview of an interference pattern. It's And now this comes to the Young's double slit experiment. Now this will be the phase difference and intensity. Again, that thing 4 I naught cos square delta by 2. So that's the same thing. And now again, by applying simple trigonometry, I would say, you can prove this r1 minus r2 is equal to ay upon s, where a is the separation between the two sources. Remember, in previous book or previous lecture, we were using small d for separation between the sources. So accordingly, your notations should be updated. So here we are using a. So this will be ay divided by s, where s is the distance between these double slit and the screen, and y is the distance of the observation point on the screen from the center of the or the line connecting center of the two sources to the screen, perpendicular distance. This is y. So I'm sure you have done it. You do it as a homework. So that is r2 r1 minus r2, and you know k naught is equal to 2 pi by lambda naught. So therefore intensity, by substituting these values, will be given by this expression. And if you try to see how does intensity vary over the screen, so this is how this graph again you would have done in your previous classes. So intensity, this is y, means the location of the point on the screen. So if y is 0, means we are on this point. So here you should see the maxima as far as these two sources are placed in symmetric manner. So means this line is representing the perpendicular crossing through midpoint of S1 and S2 to the screen. So in that case, at y is equal to 0, you should see the maxima. So this maxima refers to this location. Then at position somewhere here, now you can find out it theoretically. What is the wavelength which you are wavelength of the light which you are using? This is s upon a not 2a. So somewhere here, depending upon what are these values, you will find a minima, then maxima, minima, maxima, minima. So that is how you can locate position of maxima and minima on the screen. Correct? And this is the formula. Again, this you have done. From here you can find out, okay, where you are going to find out maxima. This is the position for maxima. For maxima, this function has to be maximum, and accordingly you can find out this thing, or this gives you, this formula will give you the location for maxima on the screen. Fine. And if you want to find out fringe width, that you already again have done in your previous classes, the fringe width will be s lambda naught divided by a. So one interesting thing to notice here is that fringe width is directly proportional to s, means farther is the screen from the double slit, more will be the fringe width, and of course directly proportional to lambda. It is inversely proportional to a, the separation of the two sources. So if the two sources are close to each other, the fringes will be what? The fringes will be narrow. So delta y will be small. So means to obtain narrow fringes, the two sources should be very close to each other. If they are very far from each other, the fringes will be very broad. And if the fringes are broad, then what will happen? If the fringes are broad, the intensity will not be that much, right? So you may not find out a very good quality fringes, which may not be visible. Okay, now sorry for their announcement. Okay, Now, there was one question put by some student: what will be the effect of slit width? What if these two slits are not very narrow, and if they are very large in size? So here is a proper answer to that. Finite size of the slit, what will that do? If the slit is of finite size, we shall see the diffraction pattern because of single slit, right? And now since we have two slits of a finite size, so the resultant pattern is going to be a mix of diffraction as well as interference. So this is the resultant. So I'm not going to do the derivation here right now, but this is what will be the intensity in that case if you have slit of finite size. So if d is the size of the slit, say finite size of the slit, and now this has been taken from the second book actually, which we are already following, and small d is the separation. So the notations have been changed a little actually. So in that case, this is the same formula. So this component refers to the interference part, and this component refers to the diffraction part. So the overall intensity is going to be the resultant of the two, where sine c is a function which is defined by this. Again, I'm not going to detail. How will this practically look on screen? So this will be superposition of the two things actually. I mean, this will be a resultant of the two. One is interference. So this line, this one, is representing the interference. If the slits were really of a finite size, were of a very small size, in that case we should obtain this one. In that case, if the slits are of very small size, then d approaches 0, and if d approaches 0, then this function will approach to 1. You can find out this one from here. So limit say alpha approaches 0, sine alpha upon alpha is 1, that one. So this will be 1, and it will be purely interference, correct? And second is diffraction. So this one is a diffraction term. This peak is giving you the diffraction. So the resultant will be what? The product of the two. So what will happen? Central maxima is maxima, as usual it should be. And what will happen is that the next maxima, which in interference should have highest intensity, and intensity should be equal. There should not be any variation of intensity if it is purely interference. Now if slits are of finite size, what will happen? The intensity will be slightly reduced here, then slightly reduced here further, and so on. Now you should say, then why can't we say it just a purely diffraction? What is the difference? I mean, in case it would be a single slit, then you should see similar kind of thing. No, in that case you should see one maximum, and minimum would be if at this point, this, just forget about this theta, this has been taken from some other problem, but yes, this is just angle with respect to the central line, this one. This is theta actually. Fine. So in case of diffraction, you should see a broad maxima like this, and then there should be a minima, then there should be a next maxima, and so on. Now the thing is that here what we are seeing is that some interference, and it would be like, okay, maxima and fringes of decreasing intensity. Then here, if it would have been purely interference, there should be a maximum, but here you would find out there is no intensity at all, and so on. So you can find out, if you increase the size of the slits, that is what is going to happen in the pattern. Okay, so that's all for today, I think. And in next class we shall be discussing some other arrangements for interference pattern obtained by wavefront division, and those are very interesting experiments. One is Lloyd's mirror, other is Fresnel biprism. So we will be doing it in the next class. I hope I could make things clear to you in this lecture. In case there are doubts, you can feel free to come back to me or ask me by email or discussion in our Google Classroom. Till then, thank you. Stay home, stay safe.